Hello everyone, and welcome to Dr. Carminati's YouTube channel. I'm so thrilled you're here today as we dive into a fascinating and mind-bending topic, experimental realization of discrete time quasicrystals by Guanghui, he and colleagues, published in Physical Review X. Whether you're new to quantum physics or just curious about the strange world of crystals that seem to defy the rules of time and space, this video will guide you step by step through this groundbreaking discovery. I'd love to hear your thoughts, so please drop your comments below, suggest ideas for future videos, hit that like button if you enjoy this journey, and subscribe to join our community of curious minds. Let's get started. Let's begin with the first big question. What is a time quasicrystal? We need to break down a few concepts to answer this, starting with what a crystal is. Imagine a crystal like a diamond or quartz. In these materials, atoms arrange themselves repeating patterns, like tiles on a bathroom floor. If you shift the pattern a certain distance, it looks exactly the exact translational symmetry which repeats in space. Now, a time crystal takes this idea and flips it into the dimension of time. Instead of atoms repeating in space, a time crystal involves particles repeating a motion pattern over time, even when in their lowest energy state. This means the particles keep moving in a predictable cycle without losing energy, which is pretty wild because it seems to defy the laws of physics as we know them. A time quasicrystal, however, adds another layer of complexity. While a regular time crystal repeats its motion in a simple, predictable rhythm, like a metronome ticking back and forth, a time quasicrystal doesn't repeat similarly. Instead, it follows an ordered pattern that never exactly repeats, much like a quasicrystal in space. Let's unpack that. A quasicrystal in space has atoms arranged in a way that fills all available space but never repeats its pattern. For example, a quasicrystal might show five-fold symmetry. Think of a star with 5 points, which is impossible for regular crystals because they can only have 2, 3, 4, or 6-fold symmetry due to the rules of tiling. A time quasicrystal applies this idea to time. Its motion follows a precise but non-repeating pattern, vibrating at multiple frequencies that interact uniquely. To create a time quasicrystal, scientists at Washington University in St. Louis, led by Chong Zhu, used a tiny piece of diamond, about a millimeter wide. They zapped it with nitrogen beams to knock out some carbon atoms, leaving empty spaces called nitrogen vacancy centers. Electrons then filled these spaces, creating a quantum system where the particles could interact. The researchers applied microwave pulses to these electrons, setting them into a rhythm that remained unchanged over time. This rhythm, driven by the microwave pulses, formed the time quasicrystal, a new phase of matter that cycles through patterns in time without ever settling into a simple, repeating loop. It's like a dance with intricate steps that never quite loop back to the starting point. Yet the dance remains perfectly choreographed. Now that we understand what a time quasicrystal is, let's explore how it impacts quantum technology. Quantum technology is a field that uses the strange rules of quantum mechanics, like superposition, where particles can exist in multiple states at once, or entanglement, where particles become linked across distances to build powerful devices. Two areas where time quasicrystals show big promise are quantum computing and quantum sensing. Let's start with quantum computing. In a quantum computer, information is stored in quantum bits or qubits, which are incredibly delicate. They lose their quantum state easily due to interference from the environment, a problem called decoherence. Time quasicrystals could help solve this by acting as a kind of quantum memory. Here's how that works. Like a regular time crystal, a time quasicrystal can theoretically keep cycling through its patterns forever without losing energy. This stability comes from the fact that it's in its quantum ground state, the lowest energy state possible, meaning it doesn't need external energy to keep going. Researchers, including Chong Zhu, suggest that this property makes time quasicrystals ideal for storing quantum information over long periods, much like RAM in a classical computer, but for quantum systems. Imagine a quantum computer that doesn't forget its calculations because its memory stays stable indefinitely. The kind of breakthrough time quasicrystals might enable. The 2025 study by Zhu and his team marks a key step toward this goal, as they created the first true-time quasicrystal, showing that such a system can exist and maintain its unique behavior. Beyond computing, time quasicrystals could revolutionize quantum sensing. Sensors detect tiny changes in things like magnetic fields, temperature, or gravity, and quantum sensors use quantum effects to achieve incredible precision. Time quasicrystals are especially sensitive to their environment because their non-repeating patterns uniquely respond to external changes. This sensitivity makes them perfect for building ultra-precise sensors that don't need recalibration or external power. For example, a time quasicrystal sensor could measure multiple frequencies simultaneously, giving a detailed picture of a quantum material's behavior. While scientists can't yet use time quasicrystals to tell time precisely, they can make them tick in a controlled way, which is a crucial first step toward developing these advanced sensors. Let's shift gears and explore the broader question: what other applications might quasicrystals have beyond time quasicrystals? To answer this, we must look at quasicrystals in general, those aperiodic structures that don't repeat in space. Quasicrystals, first discovered by Dan Shechtman in 1982, are often made of metallic alloys like aluminum, copper, and iron. Despite being metals, which are usually good conductors, quasicrystals conduct electricity poorly due to a gap in their electronic structure, a phenomenon tied to the Hume-Rothery rule. This rule explains how their atomic arrangement creates a pseudo-gap at the Fermi level, reducing the number of electrons available to carry current. This property makes quasicrystals useful in applications where you want to control electrical or thermal conductivity. One practical application is in coatings. Quasicrystals have low surface energy, meaning they resist sticking to other materials and are highly resistant to scratches. These traits make them ideal for coating everyday items like non-stick frying pans or surgical tools. For example, a quasicrystal coating on a frying pan can outperform Teflon, providing a durable, non-stick surface that lasts longer. Their hardness and low weight also make them valuable in composite materials, where they can reinforce steel to make it as strong as armor while keeping it lightweight. This combination of strength and lightness has sparked interest in aerospace, where quasicrystal-enhanced alloys could lead to stronger, lighter aircraft parts. Quasicrystals also show promise in energy technology. Icosahedral quasicrystals based on titanium can store up to 2 hydrogen atoms per metal atom, making them candidates for hydrogen storage in clean energy systems. Hydrogen is a promising fuel because it produces only water when burned, but storing it safely and efficiently is a challenge. Quasicrystals could provide a solution by offering a stable, high-capacity storage medium. Additionally, their optical properties are intriguing. Quasicrystals reflect light in unique ways due to their aperiodic structure, maintaining a nearly constant reflectivity across a wide range of wavelengths, from 300 nanometers to 15 micrometers. This makes them potential candidates for selective solar absorbers in photothermal converters, which turn sunlight into heat for power generation, or for infrared detectors that sense heat signatures. Another exciting application lies in photonics, the science of light. Photonic quasicrystals, where the lattice points are spaced much farther apart, from micrometers to centimeters, can manipulate light in ways regular crystals can't. Their aperiodic structure allows them to trap and route light from all directions, creating an afterglow effect. This property could lead to innovations like broad wavelength reflectors or even camouflage technology. Imagine a material that bends light around an object, making it invisible by mimicking the periodic patterns of a quasicrystal. While this sounds like science fiction, researchers are exploring these possibilities, and quasicrystals might one day make such technologies real. Quasicrystals also have potential in medical applications. Their biocompatibility, low friction, and corrosion resistance make them suitable for bone repair and prostheses. For example, a quasicrystal coating on a hip implant could reduce wear and tear, extending the implant's lifespan. In 3D printing, quasicrystals are being used to create lightweight, strong structures with complex geometries thanks to their aperiodic lattice patterns. These structures could replace traditional designs like honeycombs in engineering, offering new ways to build everything from bridges to spacecraft components. Let's not forget the recent discovery of superconductive quasicrystals by researchers at the University of Toronto and MIT in 2024. Quasicrystals are normally poor conductors, but this breakthrough showed that certain quasicrystals can become superconductors, materials that conduct electricity with zero resistance under the right conditions. This could lead to more efficient electronic devices, reducing energy loss in everything from power grids to microchips. The aperiodic nature of quasicrystals might also inspire new designs in macroscopic engineering, where large-scale structures mimic quasicrystal patterns to achieve unique physical properties, though these ideas are still in early stages. We've covered a lot today. The definition of a time quasicrystal as a non-repeating, ordered pattern in time, its impact on quantum technology through potential applications in quantum computing and sensing, and the broader uses of quasicrystals in coatings, energy, photonics, medicine, and more. I hope this journey has sparked your curiosity about these incredible materials and their role in shaping the future. Let's keep the conversation going. Share your thoughts in the comments. Maybe you're wondering how quasicrystals could change space travel or have an idea for our next video. Hit that like button if you learned something new and subscribe to stay in the loop. Thanks for watching, and I'll see you in the next one.